Welcome to section 5.4, Conditional Probability and the General Multiplication Rule. So in section 5.3 we looked at independent events, but many events are not independent. For instance, drawing two cards are dependent events. And again, when we talk about dependency and independent events, we're talking about probability and the effect on each event. So what we draw, if we're talking about two cards, the second time for our cards is affected by what we draw the first time. So we call these conditional events. So let's look at a quick example. Let's look at the probability that a woman has high cholesterol. All right, in general, this probability would be really hard to calculate because we know high cholesterol is affected by a lot of different things. It's affected by your diet, it's affected by your weight, genetics, all of this stuff. So a woman that has high cholesterol, that probability, that wouldn't tell us too much information. Something that would be more telling would be something like the probability of a woman with high cholesterol and we can focus on diet. So let's say something like given a, have you heard of the SAD? It's an acronym, Standard American Diet. They call it, the acronym is SAD. So Standard American Diet, this means like maybe there's fast food included in that, a lot of convenient processed meals, stuff like that. And then we could compare that to a woman, the probability of a woman with high cholesterol. And now let's say given a plant-based diet, so I'm just going to say that's a vegan diet. And if your diet is plant-based, cholesterol only comes from animal products. So if you have a plant-based diet, it means there's no cholesterol in your diet. So these probabilities are going to be very different given the diet. And so these probabilities would paint more of a picture. And again, that's because cholesterol levels and diet are dependent. Their probabilities are affected by one another. And so we say these are conditional events. Okay, and so we're going to be focusing on conditional probabilities in this section. And so we're going to rewrite this statement. Probability a woman has high cholesterol given a vegan diet. And we're going to write that given like this. So we could say high cholesterol, a woman has high cholesterol. Given, we write it as a line, given like a vegan diet or a SAD diet. All right, so let's see. So this is our notation. So again, that line right there means given that event has occurred. Okay. So let's move right along. We're at the conditional probability. So this is what we just wrote. Probability of F given E. So the probability of event E, probability of event F given event E has already occurred. So let's look at our first example. So suppose that we draw a card from a standard deck of cards. What is the probability that we draw a 2? All right, so let's look at that first part, probability that we draw a 2. Well, how many 2s are in a deck of cards? There's 4. All right, and how many are in our sample space? There's 52. All right, so the probability of drawing a 2 is 1 out of 13. And now suppose that we draw a second card after we draw a 2 of hearts. All right, now what is the probability that we draw a second 2? Okay, so let's go back to our notation from our definition, F and E. So we want to know the probability of F given E, and let's define those two events like this. So we want to know the second part, the probability that we draw a second 2, given that we just drew a 2 of hearts. All right, whoops, that's the wrong notation. There it is. Okay, so we know that if we were to draw, let's break that one down. This was on the very first draw, this was our outcomes in event E, right? All of our 2s. And then we'll do the 2 of spades at the very end. Okay? And then we drew a 2 of hearts. Okay, so now let's think about how many hearts are left. So we're going to draw a second 2. So how many are left if we already drew a 2 of hearts? Well, there's 1, 2, 3 options left. And if we've already drawn 2 of hearts and we have the 2 of hearts in our hand, how many cards are left in the deck of cards? It's 51. All right. So drawing a second card, a second 2, would be 3 out of 51. And that's examples of conditional events. Okay, so let's continue on. And we're looking at conditional probability rule. All right, so if E and F are any 2 events, our conditional probability rule is going to be as follows. All right, so we say this as the probability of F given E, probability of F given E, and I'll write that down again in just a second. So it's the number of stuff in F and E over the number of stuff of E. So notice when we look at conditional probability, the denominator is our sample space. So conditional probability, the denominator is our sample space. We're making our sample space smaller. Now our sample space is just with event E. All right, and we can also look at this like in terms of probability. So something like that. All right, so what I just said is this next part, this is like our new sample space for conditional probability. So that's one way to view this. All right, and then this first part, just to help orientate ourselves, probability of F, we're still looking at the probability of F over this new sample space. So it's still a probability of F over a new sample space. All right, and then finally, how we say this, we say the probability of F, right, given E. And then kind of in our head, we can think has already occurred. All right, and then finally, some people like to look at Venn diagrams. So let me just do a little off to the side. As far as Venn diagrams go, I think, let me put it right here underneath. All right, so as far as Venn diagrams go, maybe this is event F. And here comes event E that's already occurred. So again, what we're saying is that, and the whole thing is in the sample space, but if E has already occurred and we're looking at the probability of F given E, it means we're shrinking our sample space to this highlighted part in blue. And so the probability of F given E is going to essentially be the probability of this overlap in E. All right, so that's our nice little visual. We can also see this visual when we're looking at a table. So let's look at example 2. So this says that a survey was conducted by the Gallup organization in which 1,017 adult Americans were asked, which of the following statements comes closest to your belief about God? You believe in God, you don't believe in God, but you do believe in the universal spirit or higher power, or you don't believe in either. And then the results of the survey were organized by region of the country and are given in the table below. All right, so first one, what is the probability that a randomly selected adult American who lives in the East believes in God? All right, so we want to know the probability that a randomly selected adult American who lives in the East believes in God. So that means we're going to be focusing on this row, because this row, the top row, the East row, we're limiting our sample space to just people who live in the East. All right, so let's write this out in terms of our definition, our conditional probability definition. And again, we can think, as far as the order goes, what is the probability that a randomly selected adult American who lives in the East believes in God? So we're finding the probability of some person who believes in God. So the probability of someone believing in God. All right, and then that tells us we're going to write believes in God first, because it's the probability that someone believes in God. And now the next event we write out is the new sample space. And the new sample space is an American who lives in the East. All right, so again, let's stick with our formula. So according to our formula, we're going to count up the number of people who believe in God and live in the East. And that's that one right there, believing in God and living in the East. And we're going to divide it out by our new sample space, which is people who live in the East. All right, so let's do our calculations. One's already calculated for us. It's the 204. And then people who live in the East, well, we don't have a total column. We would have to do the math ourselves. So it's people that live in the East is 204 plus 36 plus 15. So 255. All right, and we can leave it like that. You guys can write 0.8, something like that. All right, so our first conditional probability for this example. Let's look at the next one. So it's really similar. What is the probability that a randomly selected adult American who believes in God lives in the East? All right, so now we want to know the probability that a randomly selected adult American who believes in God lives in the East. So again, it's the probability that someone lives in the East. So I'm saying it like that. I'm emphasizing that so we can write out our conditional probability correctly. Essentially, we want to know the probability of someone who lives in the East. Right? Given, or what's our new sample space, given that that American believes in God. Okay, and so our new sample space is going to be people that believe in God. So let's write this out. So it's still, we're going to be using that 204. So the amount of people that believe in God and live in the East. But our new sample space now is people that believe in God. How many believe in God? All right, so let's see. We have 204 as before. And now the amount that believe in God, we're going to have to add up our column totals. So 204 plus 212 plus 219 plus 152. So if we add all of those up, we would get 787. All right. So we can leave it like that, or we could put that into our calculator. And about 0.26. All right, so just breaking these numbers down, this first one is saying about 80% of people that live in the East believe in God. And this is saying that 25% of the people 26% of the people in our survey that believe in God live in the East. All right? So that's kind of a even breakdown if there's 4 categories, right? Let's continue onward with our conditional probability examples. So this next one. So in 2005, 19.1% of all murder victims were between the ages of 20 and 24. Also in 2005, 16.6% of all murder victims were 2 to 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24 years old? All right, that last sentence always tells us what we want to find. So we want to find the probability that a randomly selected murder victim from 2005 was male, given the victim is 20 to 24 years old. So I always like to write out what we're trying to find. We want to find the probability that this murder victim was male, right, from a specific sample space. So just from the 20 to 24-year-old demographic. All right, so we wrote that probability out. That's a conditional probability, right? That given word is our keyword. So we know we can find this by looking at the probability that the victim was male and 20 to 24 years old. And again, our sample space is the probability that the murder victim is between 20 to 24 years old. All right, so out of all these murder victims, we're looking at the snippet that was male in this age group. All right, so let's start filling in our information. The top male and 20 to 24, that's like saying 20 to 24-year-old males. So the top is 16.6. And the probability that the murder victim is in that age group is 19.1. All right, this example, we're using our probability formula versus our number formula like the example 2. And then we actually have all this information. So we're going to put this in our calculator and we get our solution for this problem. And again, I always like to put it back in the same format it was given to us. So I'd actually say that 86.9% of all the murder victims between 20 to 24 years old were male. All right, so something's going on there because we know that about only 50% of the population is male. So that's high for that demographic. Okay, so we're ready now to talk about our general multiplication rule. And we're going to get it from our conditional probability. So just as a little scratch work, let me remind you, because it's been such a long time, of our conditional probability rule. All right, and remember this is for any two events, E and F. They don't have to be disjoint, they don't have to be independent, dependent, it's for any two events. All right, and we got this. So what we're going to do now to find our general multiplication rule, which is that and statement, right? So we're finding a general rule for this one. Well, we're using our algebra skills and we're just going to solve for the numerator. So we can do that by cross multiplying. So we're going to multiply both sides by probability of E. And then we get our general multiplication rule. So we'll write that down here. So the probability that E and F both occur is the following. The probability of E and F is the probability of E times the probability of F. That was our old multiplication rule, but to make it for any events E and F, we're going to say given that E has already occurred. All right, and there you go. So if F and E are independent, we saw in the previous section that the probability of E and F is the probability of E times the probability of F. Okay, that's section 5.3. So notice that, let me bring my screen down a little bit. It's really similar, it's very, very similar to what we have for our general multiplication rule, right? So the only thing that's different is this last part. All right, and they're both really probability of F. The only thing is that for the general rule, we limit our sample space. All right, so let's talk about this. So the probability of F given event E has occurred. Well, we can see it by formula, but then intuitively, we know that if F and E are independent, their probabilities are not affected by each other. So the probability of F given E has occurred, well, F doesn't care about event E. So its probability is not going to change. So the probability of F given E, if these are independent, is just going to be the probability of F. So we can justify this intuitively and then also by the formula as well. But what this does give us is a way to determine if two events are independent. So if two events are independent, so their probabilities are not affected by the other event, we have the following. So the probability of F given E has occurred. Well, again, the events don't care about each other, so that's just going to be the probability of F. Likewise, we can also say the probability of E given event F has occurred will just be the probability of E. All right, those are one and the same. All right, so let's look at some some multiplication rules for any two events. So we'll go to the next page. So a committee consists of 4 women and 3 men. The committee will randomly select 2 people to attend a conference in Hawaii. That sounds nice. Find the probability that both are women. Okay. So again, I always like to start out by writing what we're trying to find. We are finding the probability that both are women. I like to translate both to just saying the first and the second are women, because now I have my and when we think and, our operation is multiplication. All right, so we know that we're going to be using our multiplication rule. All right, so this is how we're going to write it. We're going to write it like this. Probability that the first is a woman times the probability that our second is a woman given the first. Here I'm just going to write W to save space. All right, so these are dependent events. And in general, and I'll write this at top, sampling without replacement, which is what we're doing, we're choosing someone to go to Hawaii, and then we're not putting them back into the sample space to sample again. We're sampling without replacement. For these small sample sizes, this automatically is a conditional event. So we can, again, we have a couple ways. We can say it's dependent, not independent, conditional. Okay. All right, so there's our rule. So let's see how we're going to calculate these probabilities. Okay, so the probability that the first one's the woman. Well, how many women do we start with? The committee consists of 4 women. All right, and how many are they choosing from the committee? Well, the committee has 4 women and 3 men. So 4 plus 3 is 7. There's 7 people to choose from on that first draw, and 4 of them are women. All right, now the second draw. If you've already chosen one person, there's 6 people left in your committee. How many are women? Well, if you chose 1 woman, then you're left with 3. So the probability that the second pick is a woman, given the first pick was a woman, is 3 out of 6. And then we can cross multiply. You can reduce first if you like. I always like to reduce. And you can reduce again. You can also do this after and reduce 12 out of 42. But however you slice it, you're going to get 2 out of 7. And then you can do a decimal approximation too. And again, in your homework and on the quizzes and exams, normally I tell you, and the homework tells you what format to put it in. All right, so there's our general multiplication rule for any 2 events. Let's look at another example. So this one has to do with independence. So the following data represents the number of traffic fatalities in the U.S. by seat location, so driver seat or passenger seat, and gender, male or female in this case. And we want to know if the events female and driver are independent. So we want to know if female and driver are independent. Okay. So again, how we determine if something is independent, we just saw on the previous page, is that if we're looking at, let's say, the probability of F, if the events are independent, then the conditional probability is going to equal just the probability of F. So that's what we're doing. And then this example is kind because they kind of walk you through that process. So let's first figure out the probability of being female in this list of fatalities. So you would go total female divided by the total amount of fatalities. So again, you're not altering your sample space because it's on a conditional probability. So you're drawing from the total. And you can approximate this on your calculator. Right, there you go. And now we'll look at the probability of being female. And we're going to limit the sample space to just the drivers. All right, so we would have to look at the probability of being a female driver. Okay, so again, we're limiting our discussion to this sample space. This is the drivers. Over the total drivers. All right, and then this is 0.265. All right, so the proportion is the same. And now, intuitively, if these events were independent, female and driver independent, then this same proportion of females, when we limit the sample space, should be the same proportion of females in the overall sample. But they're different. And we can see that they're different. All right, so we can see that the probability of being a female in these list of fatalities does not equal the probability of the females being the drivers, or out of the drivers, I should say. Okay, so we're going to conclude that female and driver are not independent. All right, and then once we determine that they're not independent, that they're conditional events, we would go back and see what kind of conclusions we can draw, right? So for instance, if the proportion of females in the drivers is smaller than the overall sample, what does that mean? Does that mean females are better drivers? Stuff like that. So it would be the beginning of a discussion. Okay. Let's continue on. We are going to be looking at least probabilities. So we have that suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. So you have this box of 100 circuits and 5 are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What is the probability that the plant manager discovers at least one circuit and rejects the shipment? All right. Key word, at least. All right, so we're going to do our at least probabilities. At least probabilities, we use the complement. Okay, so we looked at this in a previous section. So again, we start off by writing the probability we want to find. Probability at least one is defective. And we use the complement. So it's 1 minus the probability of the complement. So what's the complement of at least one defective? Well, that would be, and we talked about this before, none defective or 0 defective. So that's your first step, and then we translate from none to all. So if 0 are defective, how do we write that as all? Well, how many is she sampling? She randomly is selecting 2. So if at least one is defective, that means one is defective or both are defective, and the opposite of that is 0 defective or 2 work, both work, we'll say. Okay, so continuing on, I'm just translating this, writing out all of our thoughts. If 2 work, that means the first and the second work. All right, and then that's our and. We're thinking multiplication. I'll switch colors just to keep everything as clear as possible. So that means our multiplication rule. These are not independent events because we are sampling without replacement. So we have to use our general multiplication rule. So probability of the first works times the probability that the second works, given the first one was working. All right, so let's start writing out these probabilities. All right, so this again is the complement. 1 minus the probability that the first works. Okay, well, let's go to that first sentence. There's 100 circuits, 5 are defective. 5 are defective. So that means how many work? Good, 95. And on that first pick, the plant manager is choosing from 100. Okay, so we have a circuit in our hand that works. So that means out of 100, 99 are left because we have that in our hand. And if we chose one that works, how many are left that works? Well, 94. All right, and then we put this into our calculator. We can put it in exactly. You might need some parentheses around your fractions if you're doing it in your calculator, but we're going to approximate this to be 0.098. Okay, so almost a 10% chance of rejecting that shipment. Let's write out our solution. We always want to make sure we answer the question, what's the probability the plant manager rejects the shipment? And we could say it's a 9.8% chance of rejecting, whoops, the shipment. Okay, this next example is really similar to this example we just went over. So again, you guys can pause it and then come back and look at your solutions. All right, so we have 3 cans of regular soda were accidentally filled with diet soda. It's a tragedy. And placed into a 12-pack of regular soda. Suppose that 2 cans are randomly selected from this 12-pack. So determine the probability that both contain diet soda. So again, both is first is diet and the second is diet. And this again is sampling without replacement, so it's dependent or conditional events. So the probability that the first is diet, well, there's 3 cans of diet soda out of 12. All right, so that's the probability that the first is diet. If you have a can of diet soda in your hand, there's 2 more left in the case out of 11. All right, so we put that into our calculator, and that's about 0.045. All right, part B. Determine the probability that both contain regular soda. All right, so both regular soda, that means the first is regular soda and the second choice is regular soda. Sampling without replacement, so again, conditional statements. So we have 9 cans of regular soda out of 12. So there's the probability your first choice is a regular soda. If you have a regular soda in your hand, there's 8 regular sodas left out of 11 cans. So your probability of your second pick also being regular is 8 out of 11. And again, put that into your calculator, and we get that final probability. This last one is a little bit different. Determine the probability that exactly one is diet and one is regular. Okay, so we have to be careful with the wording here. It doesn't say that the first pick is diet and then the second one is regular. They're just saying exactly one. So that means the first pick could be diet and then regular, or the first pick could be regular and then diet. All right, did you guys hear what I said? Let's write that down. So the first one can be diet and then regular, or we could have our first pick being regular and then diet. What operation do we have with or? Good. Or is addition. Okay. So we have the addition rule and the multiplication rule. This is the probability right here that our first pick is diet. Well, there's 3 out of 12 that are diet. If we have a diet in our hand, there's 9 regulars in the box, but only 11 cans. All right, and then similar situation, if our first pick is regular, that's 9 out of 12. If we have a regular can in our hand, there's 3 diets in the box, and there's 11 cans. All right, and if we put that in our calculator, we're going to get 0.409.